In this lecture, we're going to be taking a quick look at models of foot and mouth disease in livestock. So just one word, I've decided to split the lecture on foot and mouth disease and avian influenza into two different videos. This way it's a shorter thing to look at. So, foot and mouth disease in livestock. Uh, so, first of all, let me remark that in a way where if you were living in Europe at the time of the epidemic in the UK in 2001, you heard mostly hoof and mouth disease, not foot and mouth disease. Foot and mouth disease seems to be the term that is used now everywhere, but you'll also see hoof and mouth disease. This is the same disease, it's simply a different way of calling it. Here, I will only consider single population aspects. You will see in the lecture about spatial spread that most of the work actually on foot and mouth disease is spatial in some way, in a variety of ways that I'll come back on later. But that means here I'm just going to look at three models because, well, as I said, most models are spatial in some sense, and I'll explain that later. So the first thing I want to do is whenever you're modeling a disease, you need to get a good sense of what the disease does, how it behaves. And so what I'm going to do is spend a little time going back over material that we saw in the introductory lecture and digging in a bit more into details. And then we'll go into the models and just one word of conclusion. So the brief overview is actually I'm using what I gave in the earlier lecture. So I remind you that foot and mouth disease is a severe, highly communicable viral disease of cattle and swine. It affects sheep, goats, deer, and other cloven-hoofed ruminants. Horses are not affected. Some other species are susceptible, but they don't seem to develop clinical signs of the disease. So, and we'll come back to that in a second. So, what happens is that you see fever and you see blisters like sores on the tongue and lips, on the mouth, and between the hooves. Uh, Many animals recover, but it's a debilitating disease. In a way that an animal that has been infected and recovers is not necessarily in the best shape thereafter. Again, this is part of the lecture that I gave as an introduction to diseases of livestock. I remind you that what happened is that there were about 2,000 cases in the UK, and the reason I highlight the UK 2001 outbreak is that you will see that a lot of models are actually pertinent to this outbreak. So there were about 2,000 cases in farms across the British countryside. There was preemptive culling of a large number of animals. Um, okay, so let's go back into the details. So first of all, the symptoms. So what I'll do is I was hoping to manage to make those things appear as a side note, but I haven't yet, or as a footnote for now. So I'll just show you where I'm getting my information. This is a review of Davies. Um, you'll see the references after a while. The first thing is about symptoms. So disease is characterized by lesions on the coronary band of the hooves and in the mucosa of the mouth, including tongue and palate. Um, so typically clear or straw colored fluid contain, rise of body temperature, um, and one interesting thing, and we'll come back to that in a model later, is that the lesion in some animals, like sheep, for instance, can be hard to find. And that's going to be important in modeling. Um, the disease has severity that varies a lot. It can be it can result in death or severe morbidity, um, but there are animals that heal without further damage. In terms of the host species, mostly cattle, sheep, goats, and pigs. But one of the important components, which we'll come back to when we look at spatial models, is that some species in the wildlife that can come into contact with the forementioned cattle, sheep, goats, and pigs. Some of the wildlife species may also get contaminated. Okay. So there's always that fear that these wild species will act as a reservoir for the disease. Um, yeah, you can also have it in hedgehog. Uh, It's not considered zoonotic, therefore it doesn't propagate to human beings, but human beings can be propagators. And again, when we look at spatial aspects in a later lecture, you will see that this is something that has to be taken into account. Here's another paper by Alexanderson and others about the pathogenesis and diagnosis of foot and mouth disease. Um, Most of those papers sort of overlap quite a lot, but here that paper has some pictures that I wanted to show. So these are some lesions in a cow. You can see the blisters in the mouth. You can see lesions between the hooves, between the parts of the hoof. Um, you can see lesions on the tongue here. This is in a pig. Likewise, you can see the infection in feet, and in a variety of places on the tongue and on nose. I don't remember the name in English. So a little bit more about transmission now. So foot and mouth disease has the advantage that, like as we were discussing in the earlier lecture about modeling livestock, in the case of foot and mouth disease, there is a good record of what has happened, and you will see that in some of the papers I'm citing here. So this is a paper of Jamal and Belsham, review of foot and mouth disease. And like if you're interested in foot and mouth disease, all these papers that I'm citing are on the epi side, vet epi side. But they're really interesting and a good place to go. So here is, and I'm not going to go into detail. Once again, this is my strange inverted colors that I've been using throughout. This is what the genome of a foot and mouth disease virus looks like. Okay, so we have that information, not that there's much that we do in modeling there, but it is something that is sequenced and known and etc. Going back to Davies, that we already saw, there's one thing that is really important is that the replication of viral particles is extremely rapid. When the virus has entered the upper respiratory tract of a lung, so that means the replication in the animal is quite quick, and that has consequences in terms of the propagation. Okay, and um, the incubation period can be 2 to 3 days or up to 14 days, which is quite a wide range and has consequences in terms of control, of course, of the disease. Because if you have a disease with a very short incubation period, that changes quite a lot from something that has a longer incubation period. Um, there is some pre-symptomatic infectiousness that can happen. So infected animals can become infectious before they have symptoms, clinical signs, and the excretion of the virus uh, takes place for some days. Um, and infectivity ceases when the lesions, like those blisters, etc., heal. Okay. Going back to Alex Sanderson that we've seen already, one thing that I wanted to point out, as I said, one of the advantages of animal diseases is that there is quite a lot of documentation. So here, for example, they have estimated minimum doses required for infection. So this is the amount of viral particles, the number of viral particles that is needed for infection when the infection takes place through inhalation. Okay, so when the cattle, sheep, or pigs breathe in air that is carrying um, infected particles, intradermal, intramuscular, if you put it in the nose, if you give it orally. And so you can see that the inhalation and intradermal has a minimum dose that is quite low. Okay, so it's quite infectious. Um, And likewise, this is the infectivity titers in some excretions by different, so you can see in the blood of serum how much volume there is, what viral strains were observed in those excretions, etc. So one thing that I want to point out, indeed, here you can see that there is an amount of data that is available that is quite substantial. And some models, but we're not going to look at, and there is actually very little within host modeling of foot and mouth disease. But if you were to consider models of foot and mouth disease within host, well, these would be data that would be very useful to have. Here's another paper by Arts and others. And so they're looking at viral pathways. This is an interesting little figure. This is showing you the head and start of a lung system of cows. And this is where the where the prevalence of viral particles is concentrated. So you can see here it's concentrated at the back of the mouth, for example, and then this is the high level is the light blue, and then it goes down here. Okay, so again, this is something that is observable and can be interesting to know in some context. One remark that is about spatial aspects without really being spatial. There's simply going back to Jamal, one remark is that there are different um, serotypes of a virus, and they're sort of spatially located. So in the lecture about spatial spread, we will come back to potential consequences of this spatial segregation of the serotypes. Here, this is just to say that if you're writing a model for here, for instance, then you might be dealing with, you will be dealing with a different virus from the one that you would be dealing here, and that might have slightly different characteristics in terms of modeling. Okay, so this is something to bear in mind. There's not a single serotype of a virus that's prevalent everywhere. There are different serotypes that are present. Quick word about two other reviews. I think it's two that I think are interesting. There's one by Grubman and Bakst, and from 2004. And there's one by Kitching, Hutber, and Freshfield, from 2005. And this is also, this one is interesting because they are, as you can see in the title, they are looking at factors that could be relevant when you're writing models. Okay, in terms of parameterization and etc. And at the time, just a remark in passing, Kitching was here in Winnipeg. I don't know if he still is here, but he was at the time. Okay, so now let's look at models. And as I said, there's actually most models are spatial in some sense, and I'll come back to that in a second. So what I'm going to do is go over three models of foot and mouth disease here, and the spatial ones we will see in the lecture about adding spatial aspects to these models. So first of all, I'll point out a review by Matt Keeling from 2005 about models of foot and mouth disease. This is really something you should read if you're looking to see what was done in modeling at the time, because of course, what I'm going to show you was published later than this. But again, I mean, if you read Keeling, you will see that what's important is the spatial aspect. And I'll come back to that in a second. Okay, so most of the work that you can find about modeling foot and mouth disease comes from work that was done about the 2001 UK epidemic that had some consequences also in Europe as well. And I don't know why my mouse is doing this. What's important is that most of those models, what they do, they are spatial insofar as they consider farms as the unit of analysis. And as I said, we'll come back to that in a later lecture about this. So they where most models that you have seen so far consider individuals and how they become infected, most of the work that was done at the time considers farms as individuals. So you have SIR models with farms as the infectious or susceptible individuals. Okay, and we'll come back to that. So here, what I'm going to do is I'm going to show you models that don't do that. And there's not that many of them. It's quite interesting, in a sense, a brief remark, to see how one way of doing things prevails in a given context. And here in the context of foot and mouth disease, the focus quickly became the farms, and most of the work you will find deals with farms. Okay, so the first model I'll talk about is a model by Krister, Dodd, and Ferguson. It's a paper that was published in 2012. and it's about the within-farm transmission dynamics of foot and mouth disease, focusing on the 2001 UK epidemic, but within farm. It's a discrete time model. This is We've seen a variety of types of models in the course. This is here time is days, and it's counted discretely. So they denote S of t, the number of animals on a single species farm. They will very soon, and will likewise move to a multiple species farm. But to formulate the model first, they work on a single species farm. So S of t is the number of animals, the number of susceptible animals, and N of t and j is the number of animals on the farm that at time t were infected j time units before t. Okay. So I am not sure to what extent in the course you saw this type of model. I'm not sure you have seen any. I don't remember that I talked about any, but you might have seen with others. So this is an age of infection type model. Okay, discrete time, but it's an age of infection structured model. So this means that this gives you information about the time since infection of the different cases. So they then look at the infectious load of a given farm at time t as this sum, so this P of t here, which is the sum from J0 to t. Okay, so you're looking back in time, essentially. So you're going from J is 0, so that means in individuals who were infected today, at time t today, to J equals t, which means if we're at time t here, we're going back all the way to time 0. And that infectious load on the farm is the product of this function phi of j times the number of individuals who are infected right now and were infected j time units ago. Okay. So as I said, this is an age of infection structured model. Most of the models that you will see that are written like this are written as partial differential equations models. Here, this is a little different, but the idea is the same. Okay. And so phi of j here is the relative infectiousness of an animal that has infection hj. So that means if remember, we said the duration. Well, the duration of incubation is 3 to 14 days. The duration of symptoms varies as well. But so what that gives you is the infectiousness of an individual that was infected today, yesterday, the day before yesterday, and so on and so forth. And that infectiousness, for example, if you were infected, so remember the incubation period is let's say 3 days to 14 days. So before you have been infected for 3 days, your relative infectiousness will be 0. If you're in your incubation period, phi j is 0. Then as j increases, from 0 to t, that infectiousness increases as your viremia, etc., increases, and then it decreases when your viremia diminishes. Okay, so that's a very detailed and convenient way to look at things. The initial condition they take is they say that at time 0, with infection age 0, there were I0 individuals who had infection age 0. So that's how many individuals were initially infected, and they choose to take that the initial infection only concerns individuals who were infected at time 0. Okay, so you're not looking, you could look, you see, so this is at time 0 for different ages of infection greater than 0, the infection is 0. So you're assuming that at the start of the process, all individuals are becoming infected, all the individuals who are becoming infected, so that I0 is does correspond to individuals who got infection that day. And then the initial condition in terms of the number of animals is the number of animals on the farm minus the ones who were infected at the beginning. And then the model looks something like this. So the number of susceptible, so the number of animals that aren't infected at that point is the number of animals who were susceptible at the previous time step multiplied by the maximum of this number, 1 minus beta p of t over n and 0. So why is that so? So that maximum here is to avoid, of course, things becoming negative, because this number, 1 minus beta p of t over n, has no reason to stay positive. So to ensure that the solutions, well, to stay non-negative. So to ensure that solutions remain non-negative, they use this max here. Okay, and this is essentially the probability of an infection. And so this is the probability of not being infected. This is the complement. Okay, 1 minus beta is the complement of the probability of becoming infectious. And the number of individuals who at time t have been infected for j time units, well, this is the number of individuals who at time t minus 1 had been infected for j minus 1 time units. Okay, so you're progressing these age of infection individuals through time. Okay, so I'm just saying, well, if you were infected for 2 days yesterday, then you are now infected for 3 days today. Okay, and the boundary, what like in a PV we would call a boundary condition. The boundary condition looks something like so. So the number of individuals who are at time 0, at time t, infected with infection age 0, so who become infected, is the difference between the number of individuals who are susceptible today and the number of individuals who were susceptible yesterday, because that difference tells you how S of t varied. Okay. In terms of setting infectivity, what they consider is a function like this. They have phi of j, which is theta squared j e to minus theta j. Okay, and in the figures, I'll show you one figure a little later. They consider two scenarios that they label TS1 and TS2, and one of them is saying that theta, which is essentially how long theta, the inverse of theta, is how long until the peak of infectivity. Okay, so in a two-farm case, two-species farm, they are considering cattle and sheep, for example. So they are saying in the first case, cattle become infective, reach peak infectiousness at 4 days and sheep at 5 days. And the other scenario is cattle reach peak infectivity at 3 days and sheep at 4 days. Now, I just talked about two species, so let's extend the model to a two species case. In that case, the infectious weight of a farm with two species, so cattle and sheep, is computed as follows. So f of t is the infectious weight. It's the p of t that we had before, but here what you're doing is you're taking the p for cattle and the p for sheep, and then you're weighting that infectiousness of cattle relative to sheep. Okay, this is an adaptation factor that says how much more or how much less cattle are infectious relative to sheep. And that gives you the infectiousness of the farm at that time. Now, if you consider assortative mixing, so then you're saying that essentially you can break up this infectious weight between the infectious weight for cattle and sheep, and it's actually you can see. So this is the infectious weight for cattle is the weight for cattle multiplied by how much cattle interact with sheep, and likewise the infectious weight for sheep is how much sheep interact with cattle, plus the infectious weight for sheep. And for example, if you suppose that this row is 1, you're just saying they mix homogeneously, but typically you have a herd of cattle, a herd of sheep. They don't they will interact, but they don't necessarily always mix homogeneously. So that's how you control this using this parameter. Now, one thing that's very interesting with this model, and if you remember, I pointed out when looking at the characteristics of the disease that there is, for example, in sheep, it can be quite hard to tell if a sheep is infected. Okay, so the two main sources of uncertainty in this model are that the infection times, the time at which the J, okay, the time at which an individual animal becomes infected, they're typically unknown. Okay, so I mean we can assume what they are, but their model is used very much so in a looking at the data there is from the 2001 pandemic. So in that context, they don't know when the animals became infected. Okay, and also there is that problem that I was just talking about: the fact that some infections might not be noticeable. And so what they do is they define the cumulative infectiousness by day t post-infection for each species, X being like sheep or cattle, the following way by just taking the sum of those weight of infection, and then they compute the hazard function. I believe I briefly mentioned that in the first part of the course before in 2022, sorry. I talked briefly about hazard function, I believe. What if I didn't? Hazard function is the instantaneous probability of something happening. Okay, so they have a hazard for surviving detection on a given day, and it is computed like so. Okay, and alpha is alpha that comes in here is a detection threshold parameter, and it says when you saturate your detection. I'll point out, but I won't go into the details, that they also look at what they call a hybrid farm model and a between farm model, which of course, between farm model comes back to the spatial aspects that we'll be discussing in a later lecture. And so here, these are results of finding parameters for different, so the two scenarios in terms of the time to peak infectiousness, okay, that I detailed earlier, TS1 and TS2, these are the two scenarios. And here, this is the result of parameter fitting on data, and you can see that this is initial proportion of cattle, initial proportion of sheep, the detection threshold that they find, and every time they give you a confidence interval. Okay, so this is parameterized using data from the 2001 epidemic. And they find, for instance, they can compute the daily incidence They have so the result of their prediction compared to the result of the actual data that they have. Okay. Okay. Second model I want to detail is a model that came much later by Mushayabasa, Posny, and Jin Wang. Um, so it's from 2016, and it's in MBE. So here, this is an ODE model. Um, and it considers several compartments. So it has susceptible, vaccinated, exposed, infected, carrier, and recovered individuals. And by individuals, I mean cattle or sheep or whatever. Okay, of course. Um, and the model takes the following form. So remember, these are vaccinated, these are carriers. And let me spend a little time explaining the model. So the individuals are born susceptible and they are vaccinated. So because that was one of the questions that was came after the 2001 epidemic in particular was, well, could we have vaccinated? Um, would that have helped? We'll come back again to this in a later lecture about spatial aspects because there was ideas about how you would organize this in space. But okay, so individuals come in as susceptible. All individual types are subject to death. There's a vaccination process that happens. That vaccination may wane. Okay, so you can see that there's an arrow back from the vaccinated class into the susceptible class. The vaccine is not 100% efficacious as well, so there is a certain fraction of, well, fraction, there's a certain number of vaccinated individuals who may develop the disease. And of course, there's susceptible individuals, non-vaccinated susceptible individuals who can develop the disease. Once they're in the E compartment, which if you followed some of my lectures earlier, usually I call L, but this is the exposed, or in the sense of being latently infected with the disease. Once you're in the E compartment, you can either progress to a symptomatic stage or progress directly. So you see there's this kappa here, that is the proportion of individuals who go into a asymptomatic carrier state. Okay, so the animal is infected, but it is not showing symptoms. Or it can show symptoms, and after showing symptoms, it can either progress into a carrier stage or progress into a recovered stage. And likewise, an individual that is a carrier can recover. And one thing you will see is that there is disease-induced death for both carriers and for infectious, like, so symptomatically infectious individuals. Okay, so that's what the model looks like. The parameters that they use are typically like this. So you see the exit rate, what they call the exit rate is the death and entry rate. Note that those are equal. So the exit rate is mu, vaccination rate, incubation period, that's the gamma here, the vaccine waiting rate, how long individuals remain carrier, the transmission rate for foot and mouth disease, average infectious period, there's estimates for the vaccine efficacy, and then you can see that, like those values that I didn't mention here, you have a pi 0, pi 2, pi 1 here, and those things are proportion of infectious animals that progress to carrier, proportion of infectious who succumb to foot and mouth death, Um, those who recover and expose that become carriers, and carriers who die. Okay, so these are the parameters of the model. So I'll briefly go over the mathematics. So this paper is not at all like the previous paper that was really concerned about using the data. Here, this is a mathematical modeling paper that is not really considering, let's say, not necessarily trying to be realistic, but it's interesting to see what they did. I'll very briefly summarize this. So they find a basic reproduction number that they call C or C here. They find the basic reproduction number to be this expression here, and they're able to say that when this RC value is less than or equal to 1, then the foot and mouth disease-free equilibrium is globally stable in this set, which they prove to be forward invariant under the flow. I'm not going to go into much detail because that's not necessarily the objective of this course, but so you can prove mathematically that if that RC is less than 1, all solutions go there, and if it is larger than 1, then there's a unique endemic equilibrium, and that endemic equilibrium is locally stable when RC is close to 1. So it's a complicated model, I should point out. It's a complicated model, so their conclusions in terms of, for example, the existence of an endemic equilibrium are, they're not very strong in the sense that they require, they're able to prove things when the RC is close to 1, larger than 1, but close to 1, not necessarily for larger values. And what they can do is they look in terms of beta, which is the transmission parameter, and epsilon, which is the protective factor of the the vaccine, sorry, and they get a scheme showing you what the value of RC is as a function of those two parameters. Okay. So you can see that when infection becomes when the infectivity becomes stronger, the vaccine efficacy is not really able to fight against infection, and so you get higher values of the critical reproduction number. Now, one thing that is interesting here is that they then consider the periodic case. As I said, this is a really mathematical model, more so than a epidemiological model in the sense of trying to figure out things. Here, this is what's interesting is the mathematical analysis. So they consider that beta of t is a periodic function. So this is a year period. You can see, okay, when you use something like this, you're making a function that has period 365. So they're working in days. So this is the number of days uh, for a period. And what they do is they compute R0 using methods that were developed for periodic systems. I'll point out there's work by Bakker, Wang and Zhao, and then Timi, and I think Zhao. I got a paper from him just the other day about this type of problem, but in functional equation. Here, this is just a periodic ODE, so this is, um, let's say, a simple case. I decided, because I mean, some, for those that are not mathematicians in the audience, don't worry about this. I'll point this out here. This is interesting. They explain how to compute the R0, which is much more complicated in the periodic case than it is in the non-periodic case. So I've included this brief description of the computation of the reproduction number here, as in this case. Okay, so what you have to do is you have to introduce what's called a next infection operator that looks something like so, uh, and then you find the reproduction number as the spectral radius of that next infection operator. That operator is, of course, not something easy to deal with. And so, for example, if you look at the evolution operator that comes in this operator, that y of t and t minus s, given by this expression, and therefore, uh, if you want to compute numerically, for instance, you end up using this technique. So this is just to point out to sort of mathematically inclined people here that this can be computed. Um, and for non-mathematically inclined people, yes, this could be computed as well. So some people might want to compute this, some people might just want to know that it is feasible to do so. And given this R0 that they find, they can show that if R0 is less than 1, then the foot and mouth disease free equilibrium is globally stable, again, in that set omega. But when R0 is greater than 1, there are solutions. Well, first of all, the solutions are uniformly persistent, so they never go away, essentially. And the system admits at least one positive periodic solution, which, if you think about the model, makes complete sense. You have a model in which you're assuming that the transmission rate, the beta of t here, is a function of time and a periodic function of time. This results in a system that oscillates. So it's not an intrinsic oscillation. It's what we would call an extrinsic oscillation in the sense that it is imposed by varying this beta of t. And the last model that I'm really going to take a very brief look at is a model by Noor and collaborators. It's a very recent paper. I haven't really looked at it, but I just want to go over it very briefly. It's a model of foot and mouth disease again, and they're looking at vaccination, disinfection, and quarantine. Um, and what I'll just do is show you the flow diagram of that model. So they have a susceptible, latent, infected, and recovered model. So I would say this is interesting. They use what makes me happy instead of an E. They use an L, but never mind. So they have that base model to which they add vaccination, quarantine, and there's early disinfection, which I don't exactly know how it comes into play. I think it's probably, I'm not sure exactly how it comes into play, but never mind. So this is another model for within a herd instead of between farms, and I thought, okay, I'll show that. The analysis is very classic in a sense, and like the previous paper, it is a paper that is mostly concerned with a mathematical analysis and a little bit of simulation. It is not a paper like the first one I showed, which is really trying to answer a public health question, an animal health question. And to finish, I'll just mention a quick remark about the paper. That Kitching person I was talking about earlier at some point actually wrote a paper in the review, one of the journals of the Office International des Epizooties, former name of WAHO, and it deals with the use and abuse of mathematical models. And um, they point out some of the flaws, and I'm not going to go into details, but some of the flaws with the use of models. So you have to, if you go back to one thing I was saying at the very beginning of this lecture, recall that there were about 6 million animals that were slaughtered in the UK to curb the spread of the disease, that was not uh, received positively by some people. And this paper makes an argument for the fact that some of those cuttings were determined by using models in a way that was not necessarily uh, good in the view of the authors. So I just point out this table in their paper, which I find quite interesting. So they're essentially trying to say what type of use of models you should be doing depending on your knowledge of the epidemiology of the disease and the type of data in terms of quality and quantity that you have. So essentially, they say if your epidemiological knowledge is poor and the data quality you have is poor, then a model should be used to explore hypotheses. Without going any further, right? You explore hypotheses. If, on the other hand, you're in a poor knowledge context, but you have good data or good amount of data, then you can start doing hypothesis testing. Okay, so the first one is really exploring potential scenarios. If you have better data or more data, then you can start doing hypothesis testing. If you understand well the epidemiology, but you have poor data quality or quantity, then they recommend, and I mean it's based on several other papers as well, they recommend that what you should be doing is a simplified representation of past events, and you should be careful about using models for predicting future events. And I think, agree with this or not, this is a good thing to bear in mind because we've seen a lot of modeling in the context of COVID in the human case. And indeed, keeping some of those principles in mind, I think would have helped in some instances. Now, if you have both good data or abundant data and good epidemiological knowledge, then you can do a detailed representation of past events and you can do prediction of future events. But their point is that really you should keep this table in mind when you're proceeding with modeling. Don't, don't, for example, overthink your prediction component if you have poor data or you have very little data. Okay, so I thought that was a paper that was worth mentioning because, and I should point out for those of you in public health here or animal health know this, but the mathematical modelers perhaps don't know this, but it is sometimes difficult as a modeler to get the point across, and it's good to be guarded in your promotion of what you can do. So don't oversell your capacity to do stuff, and when you're doing stuff, keep in mind these principles.